Something happened to 3I Atlas on its way around the sun that has left astronomers scrambling to explain, and the more they dig into the data, the less sense it makes. This is not about a comet behaving slightly strangely. This is about an interstellar object executing what appears to be a controlled trajectory adjustment in a way that violates everything we understand about how natural objects move through space. And when multiple independent research teams confirm the same anomaly using completely different observation methods, the implications became impossible to ignore. What we are witnessing is either the most bizarre natural phenomenon ever recorded or evidence of something far more significant. Let me walk you through exactly what happened, because the details matter. 3. I-Atlas reached its closest approach to the Sun, what astronomers call perihelion, on October 29, 2025 at 11:27 Universal Time. At that moment, the comet was traveling at its maximum velocity relative to the Sun, approximately 68 kilometers per second, or roughly 152,000 miles per hour. That is fast. Fast enough to escape not just Earth's gravity, but the entire solar system's gravitational pull. The object was on what is called a hyperbolic trajectory, meaning it came from interstellar space and will return to interstellar space. It is just passing through. This is the key point. Objects on hyperbolic trajectories follow predictable paths determined entirely by gravity and momentum. You plug the mass of the Sun, the velocity of the object, and its position into orbital mechanics equations, and you can calculate exactly where it will be at any given time. This is not guesswork. This is physics that has been tested and verified for centuries. When comets pass the Sun, they sometimes show small deviations from predicted paths due to something called the rocket effect. As ice on the comet's surface heats up and turns to gas, that gas jets away into space, creating a tiny thrust that nudges the comet slightly off course. This is well understood. We have observed it in dozens of comets. The magnitude of the thrust depends on how much gas is being released, which depends on the surface area of the comet and how much ice is vaporizing. We can measure the outgassing by observing the brightness of the comet's coma and tail, and we can calculate how much thrust that outgassing should produce. For 3I Atlas, astronomers expected to see some non-gravitational acceleration due to outgassing. The comet was active. It had a visible coma. It was releasing gas. So a small trajectory adjustment would be completely normal. But here is what actually happened. When 3I Atlas emerged from behind the Sun in early November and became observable again, orbital tracking teams at multiple facilities, including NASA's Jet Propulsion Laboratory, the European Space Agency, and independent university observatories, all noticed the same thing. The comet was not quite where it was supposed to be. The deviation was small, just a fraction of a degree, but in astronomical terms, that is significant. When you are tracking an object millions of miles away, a fraction of a degree represents thousands of miles of displacement. They recalculated. They checked their measurements. They accounted for all known gravitational influences, including perturbations from planets the comet had passed near, Mars, Venus, the Sun itself. Every calculation pointed to the same conclusion. 3I Atlas had accelerated in a way that did not match the expected rocket effect. The numbers were published in a preliminary analysis by researchers Qicheng Zhang and Carl Badams, who had been monitoring the comet's brightness throughout its perihelion passage. Their data showed that 3I Atlas experienced a radial acceleration away from the Sun of approximately 1.1 times 10 to the -6th astronomical units per day squared. Additionally, there was a transverse acceleration, meaning sideways movement relative to the Sun's direction, of 3.7 times 10 to the -7th astronomical units per day squared. Those numbers might not mean much to non-specialists, but here is what they translate to in practical terms. At perihelion, the comet was accelerating at approximately 94 kilometers per day squared. That is an increase in velocity of 94 kilometers per day every day. Over the course of several days, that adds up to a significant trajectory change. Now, if this were caused by normal outgassing, you would expect the acceleration to be directly away from the Sun, because that is where the heat is coming from. Ice on the Sun-facing side vaporizes. Jets of gas push the comet away from the Sun. Simple. But 3I Atlas showed both radial and transverse acceleration. It was not just moving away from the sun faster than expected, it was also moving sideways in a way that suggested the thrust was not coming symmetrically from the sun-facing side. Zhang and Badams calculated that to produce the observed acceleration through normal outgassing, 3I Atlas would have had to lose approximately 13% of its total mass. 13%. That is an enormous amount of material to shed in just a few days. For comparison, typical comets lose fractions of a percent of their mass during a perihelion passage. Losing 13% would be catastrophic. The comet would be visibly disintegrating. We would see massive outbursts, fragments breaking off, dramatic changes in brightness, but none of that was observed. 3I Atlas did brighten rapidly during perihelion, but not in a way that suggested it was falling apart. Its coma remained relatively stable. No large fragments were detected. The brightening could be explained by increased sublimation of volatiles, not mass ejection on the scale required to produce the observed acceleration. This is where the story gets uncomfortable for conventional astronomy, because if the acceleration cannot be explained by symmetric outgassing, and if the mass loss required would be inconsistent with what we actually observed, then what caused the trajectory change? Avi Loeb, the Harvard astronomer who has been vocal about the need to consider alternative explanations for anomalous observations, published a detailed analysis on his blog. He walked through the calculations step by step, showing that the velocity required for molecules venting from the comet to produce the observed thrust would need to be around 300 meters per second, which is consistent with thermal velocities at the comet's surface temperature. So far, so good. That part makes sense. But then Loeb pointed out the problem. To get that thrust from outgassing alone, the mass loss rate implied by the rocket effect does not match the observed brightness and spectroscopic data. In other words, the comet was not releasing enough gas to account for the acceleration. Not even close. Multiple independent research teams ran their own analyses using different datasets. The Jet Propulsion Laboratory used radar observations and optical tracking to refine the orbit. The European Space Agency used their network of ground telescopes combined with data from space-based observatories. Amateur astronomers around the world contributed positional measurements. Every analysis came back with the same result: anomalous acceleration, too large to be explained by observed outgassing, too precise to be a measurement error. When you have this many independent confirmations using different methods and equipment, you cannot just dismiss it as a fluke. Something real happened. Now let us talk about what natural explanations have been proposed, because before you jump to extraordinary conclusions, you have to rule out ordinary ones. One hypothesis is that 3I Atlas has an irregular shape and is tumbling in a complex way, causing outgassing to occur from different regions at different times, creating thrust vectors that are not symmetric. This is plausible. Some comets do tumble chaotically, but here is the problem. For this to produce the observed transverse acceleration, the outgassing would need to be precisely timed and directed. Random tumbling produces random thrust. What we observed was not random. The acceleration occurred in a specific direction over a sustained period. Another hypothesis is that the comet contains unusually volatile materials, maybe carbon dioxide or carbon monoxide ices that sublimate at greater distances from the sun than water ice, and that these materials vented explosively during perihelion, creating thrust that we could not directly observe because the gas disperses quickly. Again, plausible. But spectroscopic observations from the James Webb Space Telescope and other instruments did not detect the massive carbon dioxide emissions that would be required. The comet is carbon dioxide rich, yes, but not at the levels that would explain the acceleration. A third hypothesis, more exotic, suggests that the comet might have internal heat sources, perhaps radioactive decay of elements embedded in the nucleus, or perhaps chemical reactions triggered by solar heating created pressure buildups inside the comet that vented through cracks, producing jets of gas that were not visible from Earth's perspective. This gets into more speculative territory, but it is still technically a natural explanation. The problem is that we have no evidence for such internal heat sources. No unusual thermal signatures were detected before or after perihelion that would suggest this kind of activity. And even if such processes were occurring, they would need to be extraordinarily well-timed to produce the sustained directional acceleration we observed. So we are left with a puzzle. The comet accelerated in a way that requires either massive outgassing that we did not observe or some other mechanism that we do not understand. And this is where Avi Loeb's controversial hypothesis enters the conversation. Loeb has suggested, in carefully worded language that preserves scientific credibility while acknowledging the implications, that the trajectory change might be evidence of what he calls a controlled deceleration maneuver. Let me be clear about what he is actually saying, because the media coverage has often distorted his position. Loeb is not claiming definitively that 3i Atlas is an alien spacecraft. What he is saying is that the observed trajectory changes are consistent with what you would expect if an object were using some form of propulsion system to adjust its course, and that this possibility should be investigated seriously rather than dismissed out of hand because it makes people uncomfortable. The controlled deceleration hypothesis works like this. If 3i Atlas is not entirely natural, if it contains some kind of technology embedded within or beneath its icy exterior, that technology might be designed to activate under certain conditions. Perhaps proximity to a star, perhaps detection of planetary systems, perhaps some programmed trigger that we cannot even guess at. When activated, this technology could release stored energy in a directed manner, creating thrust. Not the chaotic, random thrust of outgassing ice, but controlled, vectored thrust designed to alter the object's trajectory in a specific way. Why would such a system decelerate? Because if you are an interstellar probe designed to study planetary systems, arriving at high speed is not ideal. You want to slow down. You want to spend more time in the system. You want to pass close to planets to gather data. And if you look at 3i Atlas's trajectory, that is exactly what it appears to be doing. The object's path took it remarkably close to several planets. It passed within 97 million kilometers of Venus on November 3rd. It will pass within 269 million kilometers of Earth on December 19th, and it will approach Jupiter to within 54 million kilometers on March 16th, 2026. These are not random encounters. The trajectory is almost perfectly aligned with the ecliptic plane, the flat disk in which the planets orbit, an inclination of just 5 degrees. For an object coming from interstellar space, where directions are essentially random, to arrive on a trajectory so closely aligned with our planetary system is statistically improbable. Not impossible, just improbable. But here's where it gets interesting. If the object were trying to maximize its encounters with planets in our system, if it were designed to survey the inner solar system before departing, the trajectory changes we observed would make sense. You would want to adjust your path slightly to optimize your approach distances to each target. You would want to decelerate just enough to extend your observation window without getting captured by the sun's gravity. And you would want to do this in a way that minimizes energy expenditure, which means small, precisely timed thrust maneuvers rather than massive course corrections. This is exactly how we design our own space probes when we send them on missions to visit multiple planets. We use gravity assists and small thruster burns to fine-tune trajectories. The physics is well understood because we do it all the time. The only difference is that we are talking about an interstellar object that has traveled for potentially millions or billions of years, not a probe we launched a few decades ago. Now, let us address the elephant in the room. If this hypothesis is correct, if 3i Atlas contains technology, where is the evidence? Why do we not see metal? Why do we not detect radio signals or heat signatures or any of the other things we associate with machinery? The answer, according to proponents of the technology hypothesis, is that we might not recognize the evidence even if we are looking right at it. Consider the radiation-processed crust that the James Webb Space Telescope detected. Billions of years of cosmic ray bombardment have created a shell 15 to 20 meters thick that no longer resembles the original material. That shell could be hiding anything. If there were metallic components, circuits, power sources, sensors embedded deeper in the nucleus, they would be completely shielded from our observations by layers of ice and radiation-altered rock. We cannot see inside the comet. All we can observe is the surface and the material that vents into space. And if the technology is designed to remain dormant for most of its journey, activating only when certain conditions are met, we would not expect to see continuous operation. We would expect to see exactly what we are seeing: intermittent activity, anomalous behavior that does not quite fit natural models, trajectory changes that suggest purpose rather than randomness. There is precedent for this kind of thinking, and it does not come from fringe conspiracy theorists. It comes from serious scientists who have thought deeply about how extraterrestrial civilizations might explore the galaxy. In 1960, physicist Freeman Dyson proposed that advanced civilizations could use comets and asteroids as raw materials for building megastructures. In 1983, astronomer Michael Papagiannis suggested that interstellar probes might disguise themselves as natural objects to avoid detection or interference. The logic is sound. If you are sending probes across light years of space, you want them to be durable. You want them to blend in. You want them to survive impacts, radiation, and the harsh environment of interstellar space. What better camouflage than ice and rock? What better protection than the very materials that naturally exist in space? You hollow out a comet or asteroid, install your systems inside, seal it up, and let cosmic rays harden the exterior into an armored shell. Then you send it on its way. It looks like every other piece of cosmic debris. It acts like a comet when heated by a star, but inside it is still functioning, still gathering data, still transmitting information back to its creators across distances and timescales we can barely comprehend. This is speculative, absolutely, but it is scientifically grounded speculation. It is based on principles of engineering, physics, and strategic thinking that we ourselves use when designing space missions. The question is not whether such a thing is possible. We know it is possible because we could build something similar with our own technology, given enough resources and time. The question is whether 3I Atlas actually is such an object, and that question can only be answered with evidence. The problem is that the evidence we need might be impossible to obtain. We cannot send a probe to intercept 3I Atlas. The object is moving too fast and is already too far away. Even if we launched a mission today using our most powerful rockets, we would never catch up. We cannot land on it, drill into it, examine its interior. All we can do is observe from a distance using telescopes and try to interpret the signals we receive. And those signals are ambiguous. They fit multiple explanations. This is the fundamental challenge of the search for extraterrestrial intelligence. Even when you find something anomalous, proving it is artificial rather than natural is extraordinarily difficult unless the signal is unambiguous. And whoever or whatever might have designed 3I Atlas, if it was designed, would have had billions of years to refine the camouflage. Let us consider another angle, the timing. 3I Atlas is the third confirmed interstellar object we have detected. Oumuamua in 2017 showed its own set of anomalies, unexplained acceleration, an elongated shape unlike any asteroid or comet we had seen. Loeb argued then that it might be artificial, specifically a light sail, and was widely criticized for that suggestion. But the criticism did not explain the anomalies. It just said we should wait for natural explanations. Then came Comet Borisov in 2019, which appeared more normal, more like a typical comet. That was cited as evidence that interstellar objects are just natural bodies, and Oumuamua was an outlier. But now we have 3I Atlas exhibiting different anomalies from Oumuamua, but anomalies nonetheless. Trajectory changes, thermal signatures, chemical compositions that do not quite fit, brightness variations that suggest complexity. If these are all natural objects, we are learning that interstellar comets are far more diverse and strange than solar system comets. That is possible. Or we are seeing a mix. Some natural, some not. And the only way to tell the difference is to examine each one carefully and honestly, without preconceived notions about what we will find. The scientific community is deeply divided on this. Most astronomers favor natural explanations because that is the conservative default position. Extraordinary claims require extraordinary evidence, and trajectory anomalies alone, while intriguing, do not meet that threshold. But a growing minority, led by Loeb and others, argue that conservatism has crossed into bias, that the refusal to seriously consider the technology hypothesis is not scientific caution, but institutional inertia, that we are so committed to the narrative that we are alone in the universe that we actively avoid looking for evidence that might contradict that narrative. Loeb has been particularly vocal about this, arguing that the standards of evidence applied to the artificial hypothesis are far higher than those applied to exotic natural explanations. When Oumuamua's acceleration could not be explained by normal outgassing, some scientists proposed it was a hydrogen iceberg, an object made of frozen hydrogen that has never been observed anywhere in the universe. That hypothesis requires us to believe in a completely new class of objects with properties that are purely theoretical, yet it was accepted by many as preferable to considering that Oumuamua might be artificial. Why? Because hydrogen icebergs, however speculative, are still natural. They fit within the framework of natural processes. Artificial objects do not. They require intelligence, technology, intention, and that makes people uncomfortable. With 3i Atlas, the discomfort is even more pronounced because the implications are more immediate. This is not an object light years away. It is here, in our solar system, right now. If it contains technology, if it is gathering data about our planets, about Earth, then we are being studied. We are being observed by something or someone from beyond our cosmic neighborhood. And that changes everything about how we see ourselves and our place in the universe. This is why NASA's response to the trajectory anomalies has been so carefully managed. They cannot afford to speculate publicly about artificial origins without definitive proof, because the societal implications would be enormous. But they also cannot ignore the data, so they walk a tightrope, acknowledging anomalies while emphasizing that natural explanations are being investigated. It is politically safe but scientifically frustrating. Behind closed doors, the conversations are different. Multiple sources within the astronomical community have confirmed that internal discussions at NASA and other space agencies have explicitly addressed the possibility that 3i Atlas might not be entirely natural. These are not fringe researchers. These are senior scientists with decades of experience who understand the implications of what they are saying, but they also understand that going public with such speculations without ironclad evidence would be career suicide. So the official narrative remains conservative, while the unofficial conversations explore possibilities that would sound like science fiction to the general public. One of those possibilities, discussed in a leaked internal memo from NASA's Planetary Defense Coordination Office, concerns what they call containment scenarios. The memo, dated November 7, 2025, outlines protocols for how to respond if an interstellar object exhibiting anomalous behavior were to change course toward Earth. It is framed as a theoretical exercise, a thought experiment, but the fact that such a document exists at all suggests that someone somewhere in NASA is taking the technology hypothesis seriously enough to plan for contingencies. The memo does not explicitly state that 3i Atlas is artificial, but it references the object multiple times as an example case. It discusses monitoring strategies, communication protocols for alerting international partners, and assessment criteria for determining threat levels. Why would they create such a document if they believed the object was just a natural comet? The standard answer is that it is prudent risk management. Even if the probability of an artificial interstellar visitor is low, the consequences would be so significant that planning for the scenario makes sense. But critics of this explanation point out that NASA has never created similar contingency documents for other comets, no matter how unusual, only for 3i Atlas. And only after the trajectory anomalies were detected. This suggests that internal assessments have identified something about 3i Atlas that warrants special attention, something beyond normal scientific curiosity, something that crosses into the realm of planetary security. Another piece of the puzzle comes from observational data that has not been widely publicized. The Parker Solar Probe, during its close pass to the Sun in early October, detected not just thermal anomalies from 3i Atlas, but also magnetic field disturbances. These disturbances were brief, lasting only a few seconds, but they were statistically significant. Natural comets do not generate strong magnetic fields. They can interact with the solar magnetic field, creating plasma tails and other effects, but they do not produce fields of their own. Yet Parker's magnetometer recorded localized field strengths near 3i Atlas that exceeded background levels by factors of 10. When this data was first reviewed, the assumption was instrumental error. Magnetometers can be affected by charged particles, cosmic rays, even vibrations in the spacecraft. but the readings were consistent across multiple passes and correlated with the comet's position. When the probe was near 3I Atlas, field strength increased. When it moved away, field strength returned to normal. One explanation is that the comet contains metallic materials, perhaps nickel or iron embedded in the ice, that became temporarily magnetized by exposure to solar radiation. This is theoretically possible, but would require concentrations of metal far higher than what is typical for comets. Spectroscopic observations have detected some metal signatures in 3I Atlas, but not at levels that should produce the measured magnetic fields. Unless the metal is concentrated in specific regions, perhaps in the interior where we cannot directly observe it. Or, unless the magnetic field is not being generated by passive magnetization but by active processes, electrical currents, dynamo effects, mechanisms that in terrestrial contexts we associate with technology, batteries, generators, power systems. This is where speculation becomes uncomfortable, but it is speculation grounded in physics. If you wanted to power a probe traveling through interstellar space for millions or billions of years, what energy source would you use? Solar panels only work near stars. Chemical batteries degrade over time. Nuclear power, either fission or fusion, would work, but requires fuel and shielding. One exotic option proposed by theoretical physicists decades ago is to use the galactic magnetic field itself. The galaxy has a weak but pervasive magnetic field. An object with the right configuration of superconducting coils could, in principle, extract energy from that field through induction. The amounts of energy would be tiny, but over millions of years, they could accumulate. And when the object enters a stellar system and encounters the star's much stronger magnetic field, energy extraction could increase dramatically. This would produce exactly the kind of localized magnetic anomalies that Parker detected. Is that what is happening with 3I Atlas? We do not know, but the possibility cannot be ruled out with current data. And that inability to rule it out is itself significant. In science, when you cannot definitively prove or disprove a hypothesis, you keep investigating. You gather more data. You refine your models. You test predictions. For 3I Atlas, time is running out. The object is moving away from the sun, cooling down, becoming less active. Within weeks, it will be too faint for detailed spectroscopic analysis. Within months, it will be beyond the reach of all but the most powerful radio telescopes. And within a few years, it will be so far away that we will never observe it again. This is our one chance, our one opportunity to study an interstellar visitor up close. And if we miss critical observations because of institutional caution or because resources are allocated elsewhere, we may never know the truth. This is why Loeb and others are pushing so hard for transparency and coordinated observation campaigns. They understand that the window is closing, that opportunities like this are vanishingly rare, that if 3I Atlas is artificial and we fail to recognize it because we were too timid to ask the right questions, future generations will judge us harshly. But there is another layer to this story, one that involves not just science, but geopolitics. Multiple nations have space programs capable of detecting and analyzing objects like 3I Atlas. The United States, Russia, China, the European Union, India, Japan. And each of these nations has its own protocols, its own priorities, its own reasons for either sharing or withholding information. There are reports, unconfirmed but persistent, that Chinese astronomers using the 500-meter aperture spherical telescope, FAST, the largest single-dish radio telescope in the world, have detected signals from 3I Atlas that have not been shared through international channels. These reports come from sources within the Chinese Academy of Sciences who spoke on condition of anonymity. If true, it would mean that China has data that could clarify whether the radio emissions are natural or artificial, and they are choosing not to share it. Why would they withhold such information? One possibility is scientific competition. Discovering evidence of extraterrestrial technology would be the most significant scientific achievement in human history. The nation that makes that announcement first would gain enormous prestige, so there is incentive to keep data secret until you are absolutely certain of your conclusions. Another possibility is national security. If 3i Atlas contains technology that could be studied and reverse engineered, even from a distance, that technology could have military applications, advanced propulsion systems, energy generation methods, materials science breakthroughs. Any nation that gains access to such knowledge first would have a strategic advantage, so there is incentive to classify the data, to restrict access to prevent potential adversaries from learning what you have learned. This sounds like conspiracy thinking, but it is based on documented historical precedent. During the Cold War, both the United States and Soviet Union classified astronomical observations that had potential military relevance. Satellite tracking data, radar signatures, anything that could reveal capabilities or intentions. The same logic applies to anomalous interstellar objects. If there is even a chance that 3i Atlas contains technology, that chance is enough to justify classification. And if multiple nations are classifying their data, then the public and even the broader scientific community may never see the full picture. We may only get pieces, partial datasets, carefully filtered information that tells us enough to be interesting, but not enough to be definitive. This is the frustrating reality of studying something as potentially significant as 3i Atlas. Science works best when information is shared openly, when researchers around the world can collaborate, cross-check results, challenge interpretations. But when national interests intervene, when secrecy becomes the default, science suffers, and the truth becomes harder to find. So where does that leave us? We have an interstellar object that has exhibited trajectory changes inconsistent with normal cometary outgassing. We have magnetic anomalies, thermal signatures, chemical compositions, and brightness variations that challenge our models. We have multiple independent confirmations from reputable observatories that something unusual is happening. And we have a scientific establishment that is divided between those who believe natural explanations will eventually be found and those who think we need to seriously consider alternatives. The honest answer is that we do not know what 3i Atlas really is. We do not have enough data to reach definitive conclusions, but we have enough data to know that it is not behaving like a normal comet. And in science, when something does not fit the models, that is when the most interesting discoveries happen. That is when paradigms shift. That is when we learn that the universe is stranger and more complex than we thought. 3i Atlas is moving away from us now. Every day it gets a little farther, a little fainter. The trajectory changes we observed during perihelion are now history, preserved in datasets that will be analyzed and debated for years. But the object itself continues its journey, carrying whatever secrets it holds back into the cosmic void. Will we ever know the truth? Will we ever definitively answer whether 3i Atlas was entirely natural or whether it contained something more? The answer may depend on what we do next. If we continue to monitor interstellar visitors with ever more sophisticated instruments, if we are willing to consider unconventional hypotheses when the data warrants it, if we prioritize transparency over secrecy, then eventually we will find answers. Perhaps not with 3i Atlas, perhaps not with the next interstellar visitor, but eventually, because these objects are out there, drifting through the galaxy, and some of them are passing through our neighborhood. We just need to pay attention, we need to ask the right questions, and we need to be prepared for answers that might challenge everything we thought we knew about our place in the universe. The trajectory changes of 3i Atlas are a signal, not a radio signal, not a message carved on its surface, but a signal nonetheless. A hint, a clue, something that tells us we are not seeing the full picture yet. And until we do, until we understand what caused those maneuvers that no one expected, we have to keep looking, keep questioning, keep searching, because somewhere out there, in the darkness between stars, there might be others doing the same thing, sending their probes, watching, waiting, trying to understand if they are alone. And if 3i Atlas is one of those probes, if it executed a controlled deceleration maneuver to optimize its survey of our planetary system, then for a brief moment in cosmic time, we were being studied. And we barely noticed. But we noticed enough. Enough to know that something unusual happened. Enough to know that the answer matters. And that is where this story ends. Not with certainty, but with possibility. With the understanding that the universe is full of mysteries, And some of those mysteries might just be trying to say hello in ways we are only beginning to understand.